Hello, everyone. Welcome to MLAS 800, Integrated Machine Learning and Autonomous Systems. And this is Learning Activity 2 within our first week here. And this is going to be an overview of neural networks, artificial neural networks, their architecture, and just a high-level comparative analysis of neural networks. And so when I say neural networks, I'm very specific, and we are going to be very specific because this is a short 8-week course, so we have a lot to pack in. And we're going to be using what's called large language models. So they're all the rage. You've probably heard them through what's OpenAI and ChatGPT and maybe Meta, the Llama architecture, maybe some others called Bard and Claude. And there's a lot of large language models. There's just been a huge proliferation of these LLMs. And let's go ahead and do we're going to do an intro into LLMs because we're going to be spending a lot of time in the deep learning world, and this is within machine learning. There's three main big buckets of machine learning frameworks. There's the unsupervised learning, there's supervised learning, and then there's deep learning. Those are the three big ones. There's also reinforcement learning, which kind of can permeate within large language models, reinforcement networks, and recurrent neural nets. And there's a lot of different variations. Large language models are at their core artificial neural networks. They're based on neural network topology. And the history of large language models actually starts back to ELIZA in 1967, and then the LSTMs in 1997, and then Stanford in 2010. And there's a big jump between ELIZA in 1967 and moving forward to what you see in 2010 at Stanford. Then the transformer architecture was pioneered I shouldn't say pioneered, but because all of the algorithms and the computational engines and hardware all existed, but it wasn't until 2017 that a transformer architecture was built, and then of course it just skyrocketed. I remember giving lectures on artificial intelligence about 7-8 years ago, and it's just exploded beyond what I had envisioned, because I was keeping track of transformer architectures and generative adversarial networks back then, and kind of how they were impacting the industry and how we were using them in the industry. To what they are today, I would have never suspected they would have gotten as advanced, but then also kind of interesting, easier to use. So anyway, GPT-3 hits the scene in 2020. OpenAI becomes super famous, and they have it's been off to the races for the last 4 years. It's been amazing how much development has occurred in this area, and accessibility too. So these large language models are definitely more accessible, and we'll find out just how accessible they are in this course. Okay, so before we get into what a large language model is, in a high level architecture of it, we'll need to get into a couple basics. One is the basics of artificial neural net, as well as the high level, just mathematics behind neural networks. And again, this isn't a math course. This isn't a theory course. This is not a programmatic, probabilistic programming course. This isn't a statistics in the weeds statistics or calculus, or we're not going to be doing any of that. So this is just high level. But the basics of an artificial neural net is based on, as you would imagine, a biological neuron. And so the learning theory is based on how what's called neuronal plasticity works. And it's this is, on the left, it's a Hebbian cell complex. The Hebbian, it was D.O. Hebb that came up with this and identified this kind of Hebbian cell complex and how it's can be used for machine learning and in creating an artificial neural net. So the idea was actually Alan Turing started to I would say operationalize it. Right, it was theorized, but then operationalized much further. And then Farley and Clark in 1954 actually created a Hebbian network at MIT. So then in a computational way, in a thinking way. I shouldn't say, maybe not thinking, but in a let's say computational way. We didn't quite get to thinking quite until that's kind of more recent. So that's the base. So what I want you to take away is that the basics of an artificial neural network comes from, so an ANN, an artificial neural net, is the basic building block of a large language model. And then so through that continuity, the large language model, and an artificial neural net, it is architecturally conceptualized through the idea of action potentials that run biologically through a neuron. So it's pretty cool. Okay, now let's jump into the mathematics behind a neural net. So again, and I'm not going to go through all of these. It's a lot. So when you look at there's each neural net has what's called an input and an output. This look familiar from what we saw from the earlier lectures in cybernetics. And so there's really, you can almost look at cybernetics and the way that they look at feedback loop systems is the same way. It's got input, output, and then you have and as interesting as it sounds, you have a transformer function in the middle. So in this case, it's there is a transfer that occurs between the inputs and through these weights, they are summated, and then they create an activation function that activates towards a particular output. Now, I know that sounds like a bunch of gibberish when I say it that way. If you're interested in learning more about this, there is a link here, freecodecamp.org. They do a great job of explaining a lot of this stuff. If you want to dive into the details of how this works computationally and mathematically, that there's a great deep learning exercise and a read that you can go through, a reading exercise that you can go through. And I think the biggest thing that you can get out of this is that if someone ever asks, like, hey, what is the math behind a neural net? It's actually linear algebra. So action potentials within a neural network are based off of linear algebra. You for the most part, it follows that path. A lot of people don't realize that, but that's a good little tidbit of factual information. More advanced versions of neural nets they do get into other math and higher, more complicated mathematical structures. But for the most part, a neural net uses linear algebra. Okay. So, architecturally, let's move on to that. That's it. That's as far as we're going to go with the math. And so we'll jump into now just an architecture overview of large language models. So at a high level, there's what's called the your recurrent layers, your feed forward, your embedding layers, and your attention layers. That doesn't mean that all LLMs follow this model, but a lot of them have these different layers. And so, and then of course, we're talking about what's called the hidden layers. So each large language model is going to have some form of underlying it, different layers within it. And so I'll have an example here that will show what that looks like. But I do want to pause for a second and then explain, like, okay, well, this is great. We've been talking about large language models for the past 10 minutes now. How does this impact us in an autonomous systems perspective? Well, the definition of an autonomous system is, again, we've said this, it's a system that is capable of being independent from a human, right? And so there are characteristics that an autonomous system and an LLM exhibit, is that they both work on data sets, and they're both self-learning, and they're both adaptable, and they both are they're both based on decision-making. They're decision-making engines, and together, right? So you will have autonomous systems, and I'll show this at the end of the video. Our learning activity, that an autonomous system can have it doesn't have to have a large language model, but we just so happen to be using that as a framework for our coursework to teach autonomous systems and intelligent autonomous systems for sure. As it relates to large language models, make it so much easier to exhibit this idea of an intelligent autonomous system. Early machine learning frameworks, especially ones that, I'd say about 10 years ago even, were very hard to explain. If we created an intelligent autonomous system, if it was in software, we would use what was called expert systems approaches, and we would use supervised versus unsupervised machine learning methods, and we use ensemble, very point specific algorithms for very specific outcomes. So, for example, if I wanted to predict human behavior in a specific environment, I would use a very specific algorithm or a specific suite of algorithms to predict a very, very specific domain-specific output. And it was very hard to kind of illustrate that decision-making and that self-learning capability in those cases. Whereas large language models, they make life so much easier because you have that very quick, fast feedback from a large language model that allows you to see the autonomy in action, right? To see the interplay between, and it'll be, by the way, a second order cybernetics. It's going to be you in the loop as you're conversing and interacting with a large language model. So there's definitely it's so much easier to illustrate an intelligent autonomous system with an LLM. So that's why it makes it very useful as a tool for this course. Okay. So, as we move on here, there's a couple things that we're gonna now start now that we've got that out of the way. Let's talk through some things as it relates to a neural net. And there's a couple things that we are going to get a little technical, but nothing that we can't handle. So there's this idea of parameterization within large language models. And a parameter is the summation of weights plus biases. So you're going to be like, what is a weight? What is a bias? So back to that diagram we had earlier of an artificial neural net, you may have noticed that there's weights and then there's this term weight, but there was no biases. Well, the bias is that big circle in the middle. So and then more specifically, it's the sum total of all what we'd call those little nodes in this network on the right. And I was almost going to add in some extra terminology, but not ready for that yet. But so that's the biases, the weight plus the biases, and we add all those together, and then we get the parameters. So all the weights here, that's all these lines. And then there's 704 combos of all of these, right? And then so that gives you your weights. And then your biases that's every one of your inputs, your hidden layers, this is your input right here. These are your hidden layers, and then this is your output. So it's 10, 16, 16, 16, 2. And then that gets you to 50, which 704 plus your biases, 50 gets you to 754 parameters. Now that's the example of a neural net with 3 hidden layers and 16 neurons each. So that's what this is. So the parameters within an LLM, when you hear that, the parameters is a measure of how large a large language model is. Yeah, and so one thing that just to clarify too, I may have I need to circle back on the biases here, the biases. So the biases is so it's not the 10 plus it's everything minus the input layer. So it's 16 plus 16 plus 16 plus 2. That's your biases. And then weights plus biases then gets you your parameters. So it's everything minus your input layer. And you can check that out. So 16 plus 16 plus 16, that should get you to 48 plus 2, which gets you to 50. And then that gets you your 50 there. So just as a FYI, just to kind of do a quick self-correction on that. It's not all of these. It's just the, again, your biases is going to be all of these minus your input nodes. And then you take that plus your weights, and then you get your total parameters. Okay, so I just wanted to get a quick correction on that. So parameters as it relates to LLMs is going to be important because it actually defines how large a large language model is. So there's some other parameters. So that's the entry point. So when you hear us talk about large language models, parameters is how many parameters, and so GPT-3, the early version of GPT-3 had 125 million parameters. So you can imagine how big that is. 12 layers with what's called 12 heads. And then GPT-3 the later version, or the more recent version, has 175 billion parameters, 96 layers and 96 heads. That's a lot. It's quite a bit. But since then there has been a lot of open, like a lot of these models have been opened up. They're open source. Llama, you can get your hands on Llama. You can get your hands on Llama 2, which is a pretty decent, hefty 6.7 billion parameters, 32 layers, 32 heads. You've got Llama 2, which is 65 billion, pretty decent size. But you've got Mistral, Quen, as well as Stable LM on the smaller side. But Stable LM has different versions of this. Each of these have different versions of them. Like there's different versions of Mistral. There's Mistral 7B, but then there's also Mistral 13B, which has 13 billion parameters, and it's quite a bit bigger. And so one of the things that in the layers, that has to do with this in the middle. It's these 3 in the middle. These 3 hidden layers, that's what that's referring to here in this. Like how many hidden layers does it have? So there's 2 things that I want to point out in when we evaluate large language models, and the ones that we're going to be working with, it's going to be Llama, it'll be Mistral. I think we'll be kind of maybe Stable LM. We'll be there's no one specific set of large language models that we'll work with all of them, and it's kind of cool part of this course. So 2 things that we're going to be working with, regardless of the language model that we're using, is this concept of heads. So in LLMs, there's this idea of the number of they're like attention operators, and they're actually technically called parallel attention operators, and they work independently within the neural net. And how many heads a large language model has, you can conceptualize them like individual brains or mini brains that a large language model has. And they're independent knowledge workers, so to speak. And so the idea is that the more knowledge workers you have, the more intelligent that large language model is going to be. So now, with that said, there is a trade-off. Now, when you create a larger product, like anything, this has to do with anything, like say the game of life, when you create a project, if you add more people to it, it complicates it. You can make more complicated things with more people, but it takes a lot more coordination, and that takes there's a lot more intense intensity to communication and sharing of information when you create more people. So it's the same idea here. If you create more knowledge workers within a large language model, i.e. you have more heads that you have to contend with, more brains within the neural network you have to contend with, that creates an overhead, a cost overhead to doing business within that large language model. And so there can be diminishing returns. So you can make something. So in other words, I can create Llama 1 with 6.7 billion parameters and 32 heads, and I can double it, and then to 65, and I can 10 times the number of parameters and go to 65 billion parameters, right? And then with doubling my number of brains I'm working with from 32 to 64. But you would think that if I make that jump, does that mean that I'm going to get a 10-fold increase in computational reasoning and output? Turns out that's not the case. So you'll get more, but not a 10x more. And certainly not a 50% more. So actually, and we'll have some stats to show here in just a minute. So, and it depends on the task you give it, right? These large language models are complicated. So there's something that I'll be talking to you about. It's called this theory of scaling. So this idea of large language models, again, when I was doing talks on this in the past, and still today, as it relates to large language models and AI in general, there's this idea that scientists are kind of testing it out, is this idea of a scaling. So as I throw more at it, when will it should make these models more performant when it comes to their ability to reason and do reasoning tasks. And we are seeing that, but again, we're seeing an increase, but it's kind of like a logarithmic, a reverse logarithmic view of it. It kind of tapers off. It's like you get this big jump when you get going to big parameterization. But then it starts to taper off as soon as it's diminishing returns. Yeah, I can add more, but then I'm squeaking out 3 and 4 and 5% more by adding and doubling, right? Which is kind of something that we have to keep in mind. And so, but the idea is that the premise of the theory of scaling is that as the models grow in size, so will their capabilities. And so we're still seeing that. But we're starting to see some diminishing returns as it relates to that. So here's some benchmarks. I didn't put all of them down, but I'm showing the parameter. So Llama 3 with 8 billion parameters versus Llama 3 with 13 versus 70. Versus Llama 2 with 70. So you can kind of see what the comparisons look like. So I've got Llama 3 with 8, and then Llama 3 with 70, and then I have Llama 2 with 7, 13, and 70. So just as a quick view of it, right? So a zero shot, GPQA zero shot as an example. As I move from Llama 2 to Llama 3, you see what happens? I have 7 billion parameters. I have almost double in parameterization, but look at the zero shot learning. It goes from 21 to 22. And so I don't really get a lot of legwork out of just strictly increasing the number of parameters. But so they kind of quickly said, hey, it's actually an architecture thing. How do we make the architecture more efficient? So they created Llama 3. And so what's interesting is they were able to get a jump in zero shot learning to 34% by reducing the parameterization. So they made it more efficient, right? They made it smarter. And some of that isn't just the parameters. It's the training data you feed it, right? That's the other part of this and again, there's a lot more we can talk through, and I'm not going to, I'll let you kind of go through that process but there are a lot of other different benchmarks. We'll learn these as we move along. So I'm just introducing you to high level topics as it relates to the evaluation and comparative analysis of large language models. But bigger is not always better, is what I'm saying. So the theory of scaling has limits, even though, we are still seeing make them bigger does create some movement. We're not seeing that in some of the tasks, right? So sometimes it does, like 7 billion, although we've got little numbers here, but we went 7 billion to 13 billion for human evaluation on zero shot, from 7.9 to 14%. Okay, but it's still bad. It's not good. But you can see that the reasoning jumped to 62% when I completely changed my architecture. And by the way, changed my data set and changed the training data that I trained on. So training like humans. So when I train a human at an early age in different tasks, then I can get different. It's the same concept, right? It's, if I have a learning machine, and humans are learning machines, if I don't feed a human data, if I don't feed it data, right, and I limit its data ability, then it's not gonna have good outputs on the other end if I just kind of make it a cybernetic machine, right? Whereas I can increase it quite a bit by changing the framework, not just the framework, but also the training data behind it. So that's what ended up happening here. And so you can see where in Llama 3, we get really good, decent results at Llama 3 at 70 billion parameters. We get some jumps, 82, 79, 81, the best scores on Llama 3 at 70 billion parameters. So there's a little bit of mix of both. In other words, architecture and parameterization and scaling kind of go hand in hand to make large language models, better. But again, there's a limit to that. So from going from 8 billion to 70 billion, you're not getting a 10x on that. You see, I do get a noticeable jump, and that's good. I'm getting about a 14% increase in MMLU 5-shot, and and almost a 20% in the human eval 0-shot. And a very minimal, and so GPQA 0-shot, the 0-shot learning is so hard to do, and that's just hard in general, and that's hard for humans to do. Let's just be clear that this is reasoning tasks that are happening here are at a level that far surpass human reasoning capabilities. So there's still there's a lot that's pretty cool here. Of course, a lot of work to be done, but okay, so this is a new field. It's still very, very ripe, and we're going to be going and learning all about these different. We'll be diving in. So this diving in and learning about large language models and in the process, an intelligent autonomous system. Okay. So last two things. And this will wrap up this week's lectures. So back to this idea of making the case for LLMs for autonomous systems. This is a perfect example. If you haven't seen this, go jump out to Figure 1. Go out to YouTube and look at Figure 1. I don't know if you've seen it, but this is using OpenAI GPT-4. This came out earlier this year, about 3 months ago. And this just kind of shows you how fast the operationalization, the integration into embodied systems research as it relates to autonomous systems is occurring. So they took OpenAI and pumped it into Figure 1 and gave it speech-to-speech reasoning capability. And they say film speed 1.0 means that it is real time as it's happening, human interacting with Figure 1, asking it to do various tasks and doing it in parallel. So when you watch this video, I highly recommend it. It's a short video, only two minutes long, and you're going to get a lot out of it because it really illustrates not only how far the AIs have become, but the integration of large language models into making a complete intelligent autonomous system. And that's really what we mean, is that an LLM is a part of an intelligent autonomous system. It is a critical piece of it. And in this case, it is a key component, but it makes it all work, where figure 1 becomes an intelligent autonomous system, a very advanced one as well. So definitely feel free. I highly recommend it. Please go out and check that out. Okay, so that brings us to the end of our lectures for this week. So the big thing is we covered large language models, the components of a large language model, the parameters, the layers, the high level on the math, right? Just not too much, but a little bit to kind of give you a little idea of how that operates. The idea of these knowledge workers that operate within a large language model. Then we compared the large language models and the different types that in the parameterization, and how that is a measurement of its capabilities, or a high level, something that's high level. You can't completely use the parameterization as a metric towards its capabilities, but it's certainly one of the first starting points. But you got to take into account other aspects of the architecture and the training data. And so we talked a little bit about that. And then, of course, we finalized this in terms of a conversation around large language models imbued within intelligent autonomous systems. Okay, that's quite a bit. We are going to end this with future trends in large language model development. And so it's really just, its next steps is enhancing and continued embodiment. There's a big push now that we've gotten, these large language models have gotten very, very good. And you'll find that they're not just for the Metas of the world, or the Microsofts, or the Googles, not just for open AIs of the world. We can download large language models to our laptops and have our own personal AI assistant. And we're actually going to do that in this course, which is pretty cool. So we'll do that, and that's going to be part of our lab exercises as we move through the course. But yeah, that's the future of this, is that we're going to be getting more and more, industry is going to be pushing to use LLMs as well as LMMs, large multimodal models. We want, I don't want to spend too much any time on talking about it in this particular lecture. There's going to be time for us to discuss LMMs down the road. But the line between LLMs and LMMs is kind of blurring, so that's why I kind of am sticking with just talking about LLMs, and I'll bring up the concept of a multimodal model down the road. So, but yeah, future trends are looking really great, right? You're going to be seeing more and more what I call embodied work happening, where we take and operationalize large language models in disconnected systems, and putting large language models in robots, and humanoid robots, and UAVs, and UGVs, and more cars, and and laptops for our own personal assistants. There's just a lot of stuff that can be done. So with that, that's where we're wrapped up for this week. I do want you to take a look at a couple things. Make sure you've got an account with OpenAI. Make sure you got an account with and make sure you've downloaded Anaconda. We'll toy around with that a little bit, and definitely test out LM Studio when you get a chance, and then we'll and it's easy to find. Just open up Google LM Studio. If you're on a Mac, there's a download for that. If you're on a Windows platform, there's a download for that. If you're on Linux, there's a download for that as well. So go check it out, and use this time to kind of absorb your surroundings, absorb the material that's been presented in front of you, as well as take some time to download those tools, and then because we'll be using those tools And as we move into next week, we'll be jumping into some labs. All right, I enjoyed it. Thanks, and we will see you next week.